So here this is a problem on torsional oscillation of a shaft disc system where there are two shafts and two shafts are connected by a gear and the gear ratio is capital N. So if the smaller gear rotates by N phi, the larger gear rotates by phi, and this shaft is fixed at the left end. So if this rotates by N phi, this rotates by phi in this direction, and this shaft disc system, this shaft and disc combination, it is free to rotate about in these two bearings. So if you look from this side and draw a projection drawing, then this is the fixed end, this is the shaft, the smaller gear, the larger gear, and here we assume that the gears have negligible mass moment of inertia compared to the disc. The disc is much heavy and it has got much larger moment of inertia compared to those of the gears and of course the shafts. So now the torque, if the torque on this gear is in this direction, the torque on this gear is in this direction, and this torque is N times this torque. So why the torques are in same direction? If you draw free body diagram of the gears, so the smaller gear applies a force in this direction on the larger gear. On the larger gear applies a force on this direction on the smaller gear. So this torque is this and this torque is also this. So this is this, this is this. So if this end rotates in phi in this direction, so this rotates phi in this direction. Now if you draw the free body diagram of the disc separately and you cut here, if you cut here, then if this is T2, then this is also T2. Now our common feeling is that if this T2 is in this direction and this T2 is in this direction, then this end rotates downwards and this end rotates upwards. But there is another possibility. If this end rotates phi and this end rotates theta, where theta is greater than phi, then also this is possible. So theta has to be greater than phi for T2 in this direction and T2 in this direction. So theta is greater than phi. That means this end has rotated more in one direction and this end has rotated less in the same direction. So there is T2 in this direction and T2 is in this direction. Now this T2 will come act on the disc in this direction, and this is the rotation of the disc, which is theta. So now we have to write the equation. So we know that T2 is equal to N T1. And what is T2? T1 is N times K1 into N. And what is T2? T2 is K2 times theta minus phi. So this equation relates theta and phi. That means K2 theta minus K2 phi is equal to N square K1 phi, or phi into K2 plus N square K1 equal to theta, or phi equal to theta divided by k2 plus n square k. Now for this disk, C minus T2 is equal to I theta double dot. Why minus? Because in Newton's law, force equal to ma, force and acceleration are in the same direction. So T2 equal to I theta double dot, where T2 and theta double dot are in the same direction. So here T2 is in this direction. So T2 in the direction of theta is minus T2 actually. So this is this. And we know T2 is K2 theta minus phi. So this is minus K2 theta minus phi is equal to I theta double dot, or I theta double dot plus K2 theta minus phi is equal to 0, or theta double dot. Okay, here we have to replace phi by theta. So this is theta minus theta y k2 plus n square k1. Here I have made one mistake. This is k2 theta. So this is k2 theta. So this is, or I theta double dot plus k2 theta 1 minus k2 by k2 plus n square k1, or I theta double dot plus k2 theta k2 plus n square. So this is n square k1 divided by k2 plus n square k1 equal to 0, or here I theta double dot plus n square k1 k2 by k2 plus n square k1 theta equal to 0, and omega n square is equal to n square k1 k2 by k2 plus n square k1, and here I. So this is the natural frequency square. Now you can also do it by energy method. So if you try it out by energy method, so if you do it, then potential energy is, for the first shaft, half k1, this is half k1 n phi square, half k1 n phi square, and the potential energy for the second shaft is half k2 theta minus phi square, and kinetic energy is equal to half I theta dot square. So now you use the relation between theta and phi. Use relation between theta and phi. That means this relation. Use this relation between theta and phi, use this relation between theta and phi and replace phi by theta, and then you do d dt p plus k equal to 0, and you get the same equation as this. So you have to do a little bit manipulation to arrive at the final form. And here a small turbo generator has a turbine disc of mass 20 kg and radius of gyration 0.15 m. So this one, and driving an armature of mass 30 kg and radius of gyration 0.1 meter. This one. So through a steel shaft of 0.05 m diameter and 0.4 m long. The modulus of rigidity of the shaft is this. Determine the natural frequency of the torsional oscillation of the system and the position of the node. The shaft is supported in bearings which are not shown, but we have shown it here. So here you have to understand one thing, that this system, the shaft is, the whole system is actually rotating at a certain speed, and this is rigid body rotation. Rigid body rotation about an axis, and on this rotation a torsional oscillation is superimposed. So it is oscillating along with rigid body rotation. So then if this end rotates due to the torsional oscillation, if this ends rotate in this direction and this end rotates in this direction, then there has to be a point inside which is not subjected to any torsional rotation. It is rotating as a rigid body about the axis, but the oscillatory motion which is superimposed on the rigid body motion, that is 0 here. In this direction some theta a here, in this direction some theta b here. So this point is actually called the node, and since this is a node, there is no torsional oscillation here. This can be taken as fixed for this part, so fixed for this part, and for the turbine part the natural frequency is this. G is the modulus of rigidity, Ja is the polar moment of area for this shaft, by La is the length of this shaft, and Ia is the mass moment of inertia of this. And for this armature you can consider it fixed here and consider this as the length. So omega b is GJB LB IB. G is the modulus of rigidity, JB is the polar moment of inertia of area for this shaft, and LB is this length, and IB is the mass moment of inertia of the armature. So now from omega t has to be equal to omega b, because since this is a single shaft, this cannot have at the same time two different frequencies, one at the left end and one at the right end. So these two have to be same. So from here we get this. So LA by LB equal to IB by IA, and total LA plus LB is given as 0.4. So from here you find out what are the natural frequencies. So thank you.